This video is brought to you by thepuzzler.com. In this video, we look at the 2021 AMC 10B. We will look at each problem, its answer, and a complete explanation of the solution. Without further ado, let's start. A note before we start. For each problem, we will try to look at the most test-taker-friendly solution that gets the job done for that problem. Problem number 1. How many integer values of x satisfy this inequality? The absolute value of x is less than 3 pi. Now pi is just the ratio of a circumference of a circle to its diameter, and it's approximately equal to 3.14. I say approximate because pi never ends, but it doesn't matter for this question since we're looking for integer values. So we have that the absolute value of x is less than 3 times 3.14, or 9.42, since 3 times 3 is 9 and 3 times 0.14 is 0.42. So we have that the absolute value of x is less than 9.42. This is only true when x itself is less than 9.42 and greater than negative 9.42. Since we're looking for the integer values, the values that work are from negative 9 all the way to positive 9. So that's 9 negative numbers, negative 9, negative 8, all the way to negative 1. Their positive counterparts, which is 18. But that would be a trick question. That would be the wrong answer. We also have to include the value 0. So it would be 18 plus 1, which gives us an answer of D. Let's move on to problem number 2. What is the value of the square root of 3 minus 2 times the square root of 3 squared plus the square root of 3 plus 2 times the square root of 3 squared? Now you might just think that we cancel out the square roots, add this up to get 6 minus 2 root 3 plus 2 root 3 and get our answer as 6. But that would be incorrect, and that is probably a very common stupid mistake that you can make on this question. Notice that 3 minus 2 times the square root of 3. So the square root of 3 is approximately 1.7 something. So 2 times the square root of 3 would be 3.4 something. Maybe even 3.5 something. But regardless, it's more than 3. So this value is negative. Now when you square it, you'll get the positive counterpart of this. So when you square it, because all squares are greater than 0. And when you take the square root of that again, no, you won't get the negative value, because whenever we see the square root sign, we only take the positive square root. It's not, when we're doing it by ourselves, like in a quadratic equation, we take the negative square root, but when it's already there, we only take the principal square root, which is the positive square root. So we have to flip the signs on this. So this is the same as 2 square root 3 minus 3 squared. Since we're multiplying by negative 1, but squaring negative 1 gives us 1. And since this expression is positive, this cancels out. For this, since 3 plus 2 square root 3 is positive, the square and the square root cancel out there too. So then we're left with 2 square root 3 minus 3 plus 2 square root 2. So instead of 2 square root 3. So instead of the 2 square root 3's canceling out, the 3's cancel out. So our answer is 4 square root 3, D. Moving on to question number 3. In an after-school program for juniors and seniors, there is a debate team with an equal number of students from each class on the team. Among the 28 students in the program, 25% of the juniors and 10% of the seniors are on the debate team. How many juniors are in the program? So we set a variable. We know that the number of juniors is j. That's what we're trying to find, the value of j. So say there's j juniors. Well, if we multiply this by 0.25, we find the number of juniors that are in the debate team. And this is equal to the number of seniors that are in the debate team. So the number of seniors is 28 minus j, because if you're not a junior, you're a senior out of these 28 students in the program. And 10% of these are in the debate team. So we have this equation. This is just a linear equation that we can easily solve. we have 0.25j is equal to 28 times 0.1, which just means that we add a decimal place in the middle, 2.8 minus 0.1j. Adding 0.1j to both sides, we get 0.35j equals 2.8. Now notice that 35 and 28 are both factors, or both multiples of 7. So we know that this will lead to a nice answer. 2.8 divided by 0.35 is the same as 280 divided by 35. The factors of 35 cancel from the top and the bottom, and this would give us, so let's cancel out the 7 first. We get a 5 here and 40 here. Cancel out the 40 and the 5 to give us an 8. So j equals 8. So there are 8 juniors in the program. Now we can double check our answer here. If there are 8 juniors, then 25% of them, or 2 of them, are in debate. And the rest, 28 minus 8, gives us 20 seniors, times 0.1 gives us 2. So since the number of seniors and juniors are the same, we meet the requirements in the problem, so we can move on to problem number 4. At a math contest, 57 students are wearing blue shirts and another 75 students are wearing yellow shirts. The 132 students are assigned into 66 pairs. In exactly 23 of these pairs, both students are wearing blue shirts. In how many pairs are both students wearing yellow shirts? So we could have 3 possible combinations here. We could have a group with blue and blue, which we know there's actually 23 of. We could have blue and yellow, or we could have yellow and yellow. Now we're trying to find the number of yellow and yellow. So we have 57 students wearing blue skirts, and since there's 23 groups here, 46 of the blue people are here. So the rest of the blue people, they can't go in this last only yellow group, they have to go in this middle group. So there's 11 blues here. This would give us our 57 total blues. And since there's the same amount of blues and yellows here, there's also 11 yellows. And more specifically, there's 11 groups here. So now in total, there's 75 yellows. And 75 minus 11 would give us 64 yellows. So these 64 remaining yellows must go in this last place, which gives us 64 yellows here. But our answer isn't 64. Since they're pairs, we have to divide by 2. So there's 32 pairs here, each with 2 yellows. So our answer for that question is B, 32. Problem number 5. The ages of Joni's 4 cousins are distinct, which means different, single-digit positive integers. So I'm going to underline that because that seems probably important. 2 of the cousins' ages multiplied together give 24, while the other 2 multiply to 30. What is the sum of the ages of Joni's 4 children? Okay, so what could be the factors of 30? So it could be 1 and 30, but no, like we underlined here, it has to be single digit. 2 and 15, no, 15 is not single digit. 3 and 10, no. We could do 5 and 6, that seems to work. And that's the only one that actually works. So the 2 of the cousins are 5 and 6. Now for 24, we have 2 choices. We can do 4 and 6, or we can do 3 and 8. But we already have the 6 here. So we cross this out and we're left with 3 and 8. So we have 3, 8, 5, and 6. It doesn't matter which cousin is exactly which, since the sum won't change. Adding this up, we get 11 plus 11, which gives us 22. That was an easy one. Let's move on to problem number 6. Mr. Blackwell gives an exam to 2 classes. Mrs. Blackwell gives an exam to 2 classes. The mean of the scores of the students in the morning class is 84, and the afternoon class's mean score is 70. The ratio of the number of students in the morning class to the number of students in the afternoon class is 3 to 4. What is the mean of the score of all these students? Now they forgot to tell us something, or they chose not to tell us something. The number of students. They gave us this ratio. But when we only have the means and the ratios, it doesn't actually matter the actual number of students. So we can just assume that there's 3 students in the morning and 4 students in the afternoon. That still maintains this 3 to 4 ratio, and it makes it simple for us. So now in the morning, the total sum is 3 times 84 plus 4 times 70. That's the total sum. And since there's 7 total people, we divide by 7. Now don't just do this multiplication, instead be smart. Notice that 84 actually divides by 7, to give us 1 and 2, so 12. And 70 divided by 7 just gives us 10. So this is 36 plus 40, which gives us 76. So that's our answer for this one. You can solve it without actually assuming the actual numbers, where you would just set it as 3x and just assume that there's x students in the morning and some other amount in the evening, just to make the ratio stay the same. But this is probably the easiest way to solve the problem. Problem number 7. In a plane, 4 circles with radii 1, 3, 5, and 7 are all tangent to line L at the same point A, but they may be on either side of line L. Region S consists of all the points that lie inside exactly one. That's pretty important. Exactly one of the 4 circles. What is the maximum possible area of region S? Let me draw a line. So we have this line right here. Now we could have a few different cases, but one thing that you probably see is that we want to separate the 49 or the 7 inch or the 7 units and the 5 units on 2 separate sides to actually maximize the area. So now let's say we have a circle here. Let's just make this 7. We can make this 7. I'll write it on the side. And on the other side, we'll have the 5. And I'll mark that here. So right now, this is 49 plus 25. 49 pi plus 25 pi. Now we could put the third one right here, which would give us 3. So now this area doesn't count, so we subtract 9 pi. And we could put the 1 circle here. So we subtract another pi, which would give us 64 pi. So 49 plus 25 minus 9 minus 1, which is 49 plus 15, or 64 pi. But notice something. This area inside, that doesn't count. So if we decide to put yet another circle into this, it still won't count. So we could take this 1 in circle and move it this way. So then we would get something along the lines of, so this would still be 3. We would have another circle here with a 1. Sorry for the messy circles. But now we subtract 9 pi, but we don't have to subtract that 1 pi since it's already included in this 9 pi. And you could also have this 3 pi and 1 pi circle inside the total 5 radius circle, or the 5 unit radius circle. But we decide it doesn't really matter. So we have 49 plus 25 minus 9, which is 40 plus 25, or 65 pi. Now, if anything confuses you about this problem, you might need to review a bit about tangency and finding the area of circles. Number 8. Mr. Zhao places all the integers from 1 to 225 into a 15 by 15 grid. He places 1 in the middle square, which is the 8th row and the 8th column, and places other numbers one by one clockwise like they show in this diagram. What is the sum of the greatest number and least number that appear in the second row from the top? So I took the liberty to draw out a bigger diagram where we can see this numbers. So now let's try filling in a few more numbers. So we know that 26 goes right here. Now this number doesn't matter, this doesn't matter, this doesn't matter, this doesn't matter. So instead, we go straight to this number. So we have 26 plus 1 plus 1, so plus 1 plus 1 plus 1 plus 1, 31. So 27, 28, 29, 30, 31. This would be 32, and going all the way to the end, we get 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43. I think this is enough numbers to try and find a pattern now. So notice that it would be nice if we could find a pattern along this diagonal right here. If we could find a pattern along that diagonal right here, we actually have some potential, because then we could be filling out this number right here, which would really help us solve this problem. So let's try finding the pattern. Look at the differences between this diagonal. 1, 7. So the difference between that is 6. What about the next two numbers? 21 and 7. The difference between that is 14. 43 and 21. The difference between that is 22. Now this should be very apparent to you. This is just the arithmetic series with first term 6, common difference 8. So the next term here would be 30, then 38, 46, 54, and so on. So now we can fill these diagonals out without having to fill in the rest of the stuff. What's 43 plus what's the next number? It's 30. So 43 plus 30, which gives us 73. And then we have 73 plus 38. So 73 plus 38, which gives us 1 here, 1 here, 1, 1, 1. 1, 1, 1. And finally we have 1, 1, 1 plus 46. That's 1, 5, 7. Okay, so now we would go this way, and this would be 1, 5, and 8. And all the way, so let me move this problem out of the way. We have 157, 158, 159, 160, 161, 162, 163, 164, 165, 166, 167, 168, 169, and 170. So notice that doesn't really matter. What does matter is the fact that this number 157 is going to be the least. And the number on the left, since this number all the way on the top left corner is probably going to be in the 200s, the number below that would be just one less, so that would be the greatest. Now we continue our pattern. So we added 46 here. Now we add in 54 to get 211. So this number right here is 211. So the number right below that would be 210. So the greatest number would be 210, and we just found the least number to be 157. 210 plus 157 would give us 3. So let's add it up. 210 plus 157 would give us 3, 6, 7. Let's see if that's an answer choice. And luckily for us, it's the first answer choice. So our answer for this question is 367. That was a long one. Let's go to question number 9. The point AB in the XY plane is first rotated 90 degrees counterclockwise around the point 1, 5, and then reflected about the line y equals negative x. The image of P after these two transformations is at negative 6, 3. What is B minus A? So now you might know this from doing math. The fact that if you reflect anything over the line x equals y, if you reflect a point A, B over the line x equals y, it'll become B over A. So if we reflect it over y equals negative x, so negative x equals y, we might get something similar, although we're not sure. So what we do is we try graphing it. So we have negative 6. Not too big to graph. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'll just draw this in, just in case we need it later for the 1, 5 point. So we have this point, negative 6, 3. And we also have this line right here, which basically goes in, or as straight of a line as I can draw. And we have this distance. So this point right here is on the line, negative 3, 3. And this is P prime, which means P after the reflections. So this is negative 6, 3. We notice that the distance is just 3 horizontally. So when you reflect over this line, this 3 horizontally will become 3 vertically. And this point will become this, which makes sense. If you think about it, this reflection makes sense. So this would be negative 3, 6. And notice this is similar. We did switch to 6 and 3. The negative sign stayed in the first term though. So that was the difference that happened. Now we draw in the next point 1, 5. 1, 2, 3, 4, 5. 1, 5. So once again, we apply the same principle. So the distance from 1, 5, in the x value, that's 4. Negative 3 to 1 would be 4. So we have the point right here, that's 4. And this distance right here would be 1. So now if you're rotating 90 degrees counterclockwise and we're trying to undo that, we would rotate 90 degrees clockwise. How do we do that? Well, we're 4 away horizontally and 1 up vertically. So instead, this time, we're going to be 1 to the right and 4 up. So this would be 1, 4. So we have 1 plus 1 as our point, and 5 plus 4. This would give us 2, 9 as our point. Which makes sense. This intuitively makes sense. This point gets reflected here, and this point, although this might not make the most sense, would reflect here, and this would be a 90-degree angle. So we have 2, 9. 9 minus 2 gives us our answer of 7. Problem number 10. This was a pretty nice problem. A pretty easy problem. An inverted cone with base radius 12 centimeters and height 18 centimeters is full of water. The water is poured into a tall cylinder with a horizontal base, whose horizontal base has a radius of 24 centimeters. What is the height in centimeters of the water in the cylinder? So in this problem, we have this inverted cone, which we know all the dimensions of, so we can actually find its volume. That would be 12 times 12 times pi. That's the area of the base, times 18, that's the height. And we divide by 3 since 3 cones can fit into a cylinder. And this is equal to a tall cylinder whose horizontal base has a radius of 24 centimeters. So 24 times 24, that's the area of the base. So 24 times 24 times pi times h. This h is really important. This is the variable that we're trying to find as the height. We don't divide by 3 since it's a cylinder. Now, once again, don't do the actual multiplication, but just use some tricks. So these two pairs of 12 cancel out from both sides, and we're left with a 2 here and a 2 here. The pi cancels out, and 18 divided by 3 is just 6. So we have 6 is equal to 4h, or 6 over 4 is equal to h. That means h is equal to 3 over 2, or 1.5. Problem number 11. This was a pretty nice problem. Grandma has just finished baking a large rectangular pan of brownies. She's planning to make rectangular pieces of equal size and shape, with straight cuts parallel to the sides of the pan. Each cut must be made entirely across the pan. Grandma wants to make the same number of interior pieces as pieces along the perimeter of the pan. What is the greatest possible number of brownies that she can produce? Okay, so for this problem, notice what the number of perimeter brownies there will be. So let's say it's m by n. Notice it's a rectangle, not a square. It's an m by n rectangular grid where we have m along one side and n along the other side. So we would have m brownies, n brownies, m brownies, and n brownies. But this is counting this corner brownie. So each of these 4 corner brownies twice. Once when we're counting this m value, and once when we're counting a m value and the other n value. That would be counting these brownies twice. So what we have is the perimeter is just n plus m times 2. And then since we counted these 4 corner brownies twice, we have to subtract them, each of them once. So we get 2 times n plus m minus 4. And this is equal to, since the number of brownies inside, so that's a very ugly drawing, but since the number of brownies inside is equal to this number, we have that this is equal to the total thing divided by 2. And the total number of brownies is n times n to n times m divided by 2. Make sure you follow through with this. It's just that if we multiply by 2, we'll get n times m, and this is just equal to the interior part, which is why this works. Multiply by 2 to get 4n plus m. So 4n plus 4m minus 8 is equal to n times m. Now you can factor out this 2 to get 4 times n plus m minus 2 is equal to n times m. Now notice that there's a factor of 4 on the left, and since we're only dealing with integers, that means our answer is going to be a multiple of 4. So here we can immediately cross out 30. We know that doesn't work. And now you can just start all the way from the right and apply just a bit of casework on the answer choices to find your answer. There might be other ways to do it, but this is probably the easiest. So say we have 64 cookies. That would mean that n times m is equal to 64, and this left side is also equal to 64. So n plus m minus 2 is equal to 16, or that n plus m is equal to 18. If n plus m is equal to 18, then we can just try out various factors here on the right side that will make the product 64 and the sum 18. So notice that both n and m must be even, so that's divisible by 4. So we have 216, which doesn't give us 64. We have 414. No, we only need products of powers of 2. So we have 6, 12, no, 8, 10. That has a factor of 5. And anything below that won't work because we'll just start repeating, switching the values of n and m. So let's try 60. So we have n plus m minus 2 is equal to, since 60 is equal to 4 times 15, it's equal to 15. So we have that n plus m is equal to 17. Okay, so now we need to find a product that multiplies to 60. So we have 16 times 1. That doesn't work. So for the previous one, I said they both must be even, but that doesn't have to be the case. One of them could be divisible by 4 and the other one not. But here we have 16 times 1, 15 times 2, 14 times 3, 13 times 4, 12 times 5. And that's what we wanted. 12 times 5 is equal to 60. So that means that 12 and 5 work, and that would give us the greatest possible answer, 60. Let's just double check to make sure it works. So 12 times 5 would mean that we have 60 cookies. Now on the interior would be 12 minus 2, since we're subtracting the outer layers. 12 minus 2 times 5 minus 2, which would give us 10 times 3, which equals 30, which should be half of 60, and thankfully it is. So our answer is 60. Problem number 12. Let n equal 34 times 34 times 63 times 270. What is the ratio of the sum of the odd divisors of n to the sum of the even divisors of n? Okay, so for this problem, we have to actually find the sum of the divisors of a number. So let's find the prime factorization first. We have n is equal to 2 times 17 times 2 times 17 times 3 times 3 times 7 times 3 to the power of 3 times 2 times 5. Basically, we have 2 to the power of 3 times 3 to the power of 5 times 5 times 7 times 17 squared. Okay, so how do you find the sum of the factors of a number? If you don't know that, make sure to watch our video on it. We have a full video on it that you can watch to find how to find the sum of the factors of any number. But basically what you do is you take each number, take it to its exponent, then you add it the lower exponent. So for example, 2 cubed plus 2 squared plus 2 to the power of 1 plus 2 to the power of 0. And so on. Basically the logic is adding up all the numbers. The logic behind this is that when you do this for each factor all the way with all the powers, then when you expand that, you'll cover each factor exactly once. Watch our video on that for a complete explanation. So now we can manipulate this a bit. What you'll notice is that if we did this all the way, for the odd factors and the even factors, it would almost be the same. When I say almost, I mean that the powers of 2 or the factor of 2 would be a bit different. So in the odd ones, we won't have a 2 cubed ever because then it will be divisible by 2. We won't have a 2 squared. We won't have 2 to the power of 1. We will have 2 to the power of 0. And then we'll have the rest of the stuff. So this rest of the stuff will stay the same on both the odd divisors and the even divisors in the multiplication, so we can cancel it out. On the bottom, we'll have 2 cubed plus 2 squared plus 2 to the power of 1, but not 2 to the power of 0, since that would mean it's odd. This is just 1 over 8 plus 4 plus 2, which gives us 1 over 14. So our answer is 1 over 14. Now this question probably seems very confusing if you've never seen this formula before, but that's the way you would go proceeding and go on solving this problem. Let's take a look at the next problem. Let n be a positive integer and d be a digit such that the value of the numeral 32d in base n equals 263, and the value of the numeral 324 in base n equals the value of the numeral 11d1 in base 6. What is n plus d? So there was a problem on bases in AMC 10A, and now we see another problem. So you can see that number 3 is just really prevalent in the AMC 10. And if you want any help in that, we have a full free course on thepuzzler.com, which you'll find a link to in the description below. But for now, let's try solving this problem. If you need a quick refresher on bases, you can watch our video on it. But this is how we would proceed solving this problem. So from the first equation, 32d in base n equals 263, we can extract the following information. So since the third digit or the third value from the right is n squared, we would have 3n squared plus 2n plus d is equal to 263. So it's looking a bit messy. Hopefully it'll get better. Now we have that 324 in base n, which is once again 3n squared plus 2n, but this time plus 4 in base n. So this is in base 10 now, equals the value of the numeral 11d1 in base 6, which is 216 plus 36 plus 6d plus 1. Wait, if we subtract this second equation or this second expression from the first expression, this n value will cancel out, just leaving us a simple linear equation. Let's do that. So we subtract this. We get 3n squared minus 3n squared, so 0, plus 2n minus 2n, which gives us 0, plus d minus 4, which gives us 263 minus 216. So 216 plus 36 plus 1 would be 216 plus 37, or 253. And 263 minus 253 is just 10, plus 60, obviously. So now, what would we do next here? We have this equation right here, and we have the fact that, one second, so just double checking everything. So we have 3n squared plus 2n plus d in base n equals 263, and 3n squared plus 2n plus 4 in base n is equal to this value, which is 216 plus 36 plus 60 plus 1. So it's always a good idea to check your mistakes while you're solving the problem instead of at the end, because they're easier to catch. So here we see that the numbers don't turn out to be so nice, so we might have made some mistake. And just like that, you'll notice that this should be a minus sign. If that's a minus sign, now we'll start getting nice numbers. So we can add 60 to both sides to get 7d. Adding 4 to both sides, we'll get 14. So d is equal to 2. So if d is equal to 2, then in this first equation, we'll get 3n squared plus 2n plus d is equal to 263, or that 3n squared plus 2n is equal to 263 minus 2, or 261. Now you could take out this quadratic and factor it or whatever, but you know that n is an integer and it's approximately 3 times squaring it. So we can try squaring 8. That's 64 times 3 plus 16. That's 180, 192 plus 16. That's too small. Let's try 81. So we have, or let's try 9 as n. So we have 81 times 3, which is 243, plus 18, which gives us 261. So n equals 9, d equals 2. So adding them up, we will get an answer of B. Problem number 14. 3 equally spaced parallel lines intersect a circle, creating 3 chords of lengths 38, 38, and 34. What is the distance between 2 adjacent parallel lines? So notice that the chords are equally spaced. Now what you have to notice or know for this problem is that when we draw a chord like this, then when we draw the next chord, so a chord is just a line connecting 2 points that are on the circumference of a circle, it will be bigger than the previous chord. And if you keep on doing that, drawing it parallel to the center, you'll see that the chord keeps on getting bigger all the way until we hit the diameter itself, which is the biggest possible chord in a circle. After that, we'll start getting smaller again. So if we have a chord, say here, it doesn't tell us specifically where, of length 38, then there's not going to be a chord of this size in this semicircle. Instead, we have to cross semicircles and go over here, because anything in that first semicircle will either be larger than or smaller than 38. So this is 38. We can let this distance equal x. Since both the chords are the same distance from O, they're both x. Now you can draw a chord with the length of 34 anywhere. Maybe we can draw it here. By anywhere, I mean you can draw it in this first semicircle or the semicircle on the bottom. And now we can make some more lines. Notice that whenever you draw a line from the center of a circle to a chord, it will actually be the perpendicular bisector. That's a very important theorem that you should know for this problem. So I'm going to draw the perpendicular bisector. So whenever a line to a chord bisects that chord, it will be perpendicular. So this is a right angle. Now let me draw in this line and let's see what we have here, a right triangle. Since it's the perpendicular bisector, this is 17. We don't know the measure of this, but we did set this as 2x. The distance between two lines is 2x. So this is 2x plus x, which gives us 3x. And we also know that this is the radius of the circle. So we have 17 squared plus 3x. Instead of calling it 3x, let's just write it as a measure of the radius and 17. So we have r squared minus 17 squared, and taking the square root of that will give us the measure of this line. We also know, so I'm gonna undo some of this stuff. We also know that this line right here, if we draw this right here, this is x, and this once again is r, and this is 19. So we have that this is equal to 3x, and the square root of r squared minus 19 squared is equal to x. And now we can easily solve this problem. First, square both sides for both the equations. So we'll get r squared minus 17 squared is equal to 9x squared. For the second equation, we'll get r squared minus 19 squared equals x squared. And now you can subtract the second equation from the first equation to get minus 17 squared, and minus minus turns into positive, so 19 squared minus 17 squared gives us 9x squared minus x squared, or 8x squared. So now this is the difference of squares, so 19 minus 17 times 19 plus 17, which gives us 8x squared. Now scrolling down just a bit, we get 2 times 36 equals 8x squared. Dividing both sides by 8, we get 36 divided by 4, so 9 equals x squared. And x equals 3. So the distance from each of the chords to the center is x. But that's not our answer. We're looking for 2x as our answer because that's the distance between each parallel line. So 2 times 3 would give us an answer of 6, and that would be problem number 14. Problem number 15. The real number x satisfies the equation x plus 1 over x equals the square root of 5. What is the value of x to the power of 11 minus 7 times x to the power of 7 plus x cubed? Now you could bash this out, make this a quadratic by multiplying both sides by x, and you'd find a nice answer at the end. But the way you would get to that answer would involve very long calculation that probably isn't worth the time for this problem on the test. Instead, we'll show you a really cool solution as to how you can tackle this problem. A special thanks to ASDF334 on AOPS for helping come up with this solution. Okay, so if you've probably seen an expression like this if you've ever done competitions like Math Counts or their preparation material like Math Counts Minis. So what you can do here is if you square both sides, x plus 1 over x squared is equal to square root of 5 squared. You can do this because we're doing the same thing to both sides of the equation. Now, one quick thing I want to review is that a plus b squared is equal to a squared plus 2ab plus b squared. This should be something that you should know on the AMC 10, but it's also something that you can come up with on the spot. And the way you can do that is by multiplying out a plus b times a plus b. And you'll still get the same expression. Okay, so let's apply the same here. We square the x to get x squared. Then we multiply by 2 times x times 1 over x. And then we add 1 over x times 1 over x, or 1 over x squared, is equal to 5. Now the x's cancel here, so that we have x squared over 1 over x squared is equal to 2. We still have a 2 on the left side, so we have to subtract 2 from both sides to get 5 minus 2 is equal to 3. Interesting. So this gave us a pretty nice answer. Okay. How can we use this? We don't have a squared term anywhere. One thing that we do notice is that for the expression that we're trying to find, there's x cubed terms everywhere. There's an x term everywhere. So what we can do is that we can factor out the x cubed to get x to the power of 8 minus x to the power of 8 minus 7 times x to the power of 4 plus 1. That seems a bit more manageable. These coefficients, or these powers, look nice. 8, 4, 0. Because it's x to the power of 0, which is 1. Let's try this, what we just did here again. So we square both sides again. And this time I won't write out the whole thing, but we know it's x to the power of 4 plus 2 times x squared times 1 over x squared, where the x squared and the 1 over x squared would cancel out. So we get x to the power of 4 plus 2 plus 1 over x to the power of 4. Which gives us 3 times 3, or 9. So x to the power of 4 plus 1 over x to the power of 4 equals 7. Now, if you weren't able to solve this problem on the test, now would probably a good time to pause the video and see if you can see how we proceed from here. I'll give you a hint. We'll use some type of substitution. Okay, did you pause it? Well, here we go. So here, what we can do is realize that this 7 right here can be switched for this expression right here. Since they're equal, we can do this substitution. And what that will do is give us this nice x to the power of 8 term, and it'll cancel out the x to the power of 4 term. Let's see if it'll do anything. This is a bit of hopeful thinking, hoping that it might do something, and it might. But it's always a good idea to check, because the MAA probably doesn't want us to bash this out, so they're probably looking for some sort of cool manipulation. Now we multiply this by x to the power of 4 and add 1. So we have x to the power of 8 minus x to the power of 4 times x to the power of 4, which is x to the power of 8. So minus x to the power of 8 plus, or minus again, 1 over x to the power of 4 times x to the power of 4. That's just 1. And then we have the plus 1. Wait, this expression right here is 0 plus 0, or just 0. That expression is 0 times x cubed. Well, anything times anything, 0 times anything always gives us 0. So this expression is simply just 0. Okay, problem number 16. Call a positive integer an uphill integer if every digit is strictly greater than the previous digit. For example, 1, 3, 5, 7, 8, 1, 1, 3, 5, 7, 89, and 5 are all uphill integers, but 32, 1240, and 466 are not. How many uphill integers are divisible by 15? Well, for this, you need to know your divisibility rules. And if you don't know that, you can check out our free number theory course on thepuzzler.com. Yes, it's a free course. I'll put a link to that in the description below. You can check that out. Or you can just get a quick refresher by watching our video on divisibility rules. Basically, for a number to be divisible by a composite number, you need to make sure that it's divisible by each of the prime factors of the composite number in general. So 15 is equal to 3 times 5. So these numbers that we're looking for must be divisible by both 3 and 5. Now, for a number to be divisible by 5, the last digit can either be 0 or 5. But if the last digit is 0, and the numbers are strictly greater, that means that they're not equal to, but actually greater than the previous digit, then what would the previous digit be? -1? No, that doesn't make sense. Our digits need to be anywhere from 0 to 9. And 0 itself is not a positive integer, so it doesn't count. So the last digit must be 5. Now we can do casework based on the number of digits there are. If 5 is the last digit and there are 5 digits, well then, for every possibility of digits, there's only one number that works. For example, here the only choice that we have is 1, 2, 3, 4, and 5. And that, since we have to put in least to greatest, would be 1, 2, 3, 4, and 5. There's no other order that we could put this in. Thankfully for us, 1 plus 2 equals 3, 3 plus 3 equals 6, 6 plus 4 equals 10, 10 plus 5 equals 15, which is divisible by 3. So this works. Now with 4, once again we have 5 at the end, but this time, we're subtracting a number from 15. And that number should be, after we subtract it, be divisible by 3. So 15 minus 1 would give us 14, no. 15 minus 2 gives us 13, no. 15 minus 3 gives us 12. 12 is divisible by 3. 15 minus 4 gives us 11. 11 is not divisible by 3. And you could just notice that by noticing that 15 is a multiple of 3. So to subtract a number and get a multiple of 3, the number that we subtract must be a multiple of 3. So that means that the only 4-digit number that works is 1, 2, 4. There's no other possibility because that won't be divisible by 3. So that gives us 1 again. Now, what about 3-digit numbers? Once again, we have 5 at the end. If we have a 1 first, that would give us a 6. To get a multiple of 3, this digit in the middle must be a multiple of 3. And the only one that works is 3. What if we have a 2 here? That would give us 7. 7 plus 1 is not a multiple of 3. We can't even have 1 since 1 is less than 2. 7 plus 3 is not a multiple of 3, and 7 plus 4 is not a multiple of 3. So that does not work. What if we have a 3 here? Then the total sum is 8. 8 plus 1 gives us 9, and 8 plus 4 would give us 12. Both of those work. But this would be a big mistake. You can't have 1. The only number that you could have is 4, because 1 is less than 3. Finally, if we have 4 here, well then there's no number that can possibly go in the middle, so that wouldn't work. So we just have 4 here. What about 2-digit numbers? So we have 2 choices here. Now, if 5 is the last digit, then either a 1 could go here or a 4. Nothing else works there. And finally, for 1-digit numbers, the last digit must be 5. And since 5 isn't divisible by 3, this doesn't work. So we have 1 plus 1 plus 2 plus 2 plus 2. Is that too many 2's? Yeah, 1 plus 1 plus 2 plus 2, which gives us an answer of 6. So 6 uphill integers are divisible by 15. Number 17, another good problem. More of a logic puzzle than a math problem. Ravon, Oscar, Aditi, Tyrone, and Kim play a card game. Each person is given 2 cards out of a set of 10 cards numbered 1 through 10, and the score of a player is the sum of the numbers of their cards. The scores of the players are as follows. Ravon got 11, Oscar got 4, Aditi got 7, Tyrone got 16, and Kim got 17. Which of the following statements are true? So looking at these statements, we can't really get our answer from these statements because they're pretty broad. Instead, we just write the possible scores here. So R, O, A, T, K. Those are their first letter initials. Got a 11, got a 4, got a 7, got a 16, and got a 17. So it's usually best to start out with the biggest number since it'll be the most restrictive. How can we get a 10? We could get it as a 10 and a 7. How can we get a 17? We could get it as a 10 as a 7, 10 and a 7, or 9 and an 8. Now, if we get it as a 10 and a 7, then how would we get a 16? The ways of getting a 16 are 10 and 6, but we can't do this since we already used a 10 here. 9 and 7, but we can't do that since we already used a 7. And that's it. We can't do 8 and 8. That doesn't work. So these two are the only two that work, and both of them don't work if we use 10, 7. So we have to use 9, 8 here. If we do that, this doesn't work, so 10, 6 works here. And now, how would we come up with 7? So we could just try a bit of casework, or just a bit of guessing and checking. What about 1 and 6? 1 and 6, so that this would give us no way to get a 4. Okay, so we can start with a 4 next. We can't have a 2 and a 2, so this must be 1 and 3. So then this must be 2 and 5. And finally, what are the numbers we're left with? 7 and 4. And those add up to 11. So checking 7 and 4 add up to 11. 1 plus 3 equals 4. 2 plus 5 equals 7. 10 plus 6 gives us 16. 9 plus 8, which gives us 17. So all of them work. Ravon was given card number 3, not true. Aditi was given card number 3, not true. Ravon was given card number 4, true. Aditi was given card number 4, no. Tyrone was given card number 7, no. So our answer is C. Okay. Question number 18. This was probably my favorite question on the test, and which is coincidental because on the A, number 18 was also my favorite question. A fair 6-sided die is repeatedly rolled until an odd number appears. What is the probability that every even number appears at least once before the first occurrence of an odd number? Now this problem is just really cool. First of all, you can just assume that the 2 appears first, then the 4, then the 6. And there's actually 3 factorial ways. You could have the 4 first or the 6 second. Basically, you have 3 choices for which even number appears first, and 2 for the second, and 1 for the third. So that would be 3 factorial, which gives us an answer, which gives us 6 possible cases. Now, on the first number, but it makes it easier for us to just look at 2, 4, and 6 than the generic case. So now on the first number, we need to have a 2, and the probability of that is 1/6. On the second number, we need to have a 4, or we could have a 2, in which case we would just re-roll. So basically, out of the possible numbers that we could have, 1, 2, 3, 4, 5, and 6. If we roll a 4, we're fine, and that's the probability we're trying to find. And if we roll a 2, we re-roll to get this set again. 1, 2, 3, 4, 5, and 6. Basically, if we roll a 2, we have to re-roll. So that roll doesn't even count. So that means that we don't even have that as an outcome. Because it's not even... in this case, we can sort of assume it's not possible to get 2 again. Even though we could roll a 2 again. In which case, we would just re-roll. So out of the 5 remaining numbers, only one of them works, which is the 4. So we need the 4. So that would be a probability of 1/5. Now, after this, for all the die rolls that we have, we can roll a 2 and a 4. They don't really matter. Basically, out of the 1, 3, 5, and 6, each of them has a 1/4 chance of appearing first, and we need the 6 to appear first. So the probability of that is 1/4. So we multiply to get 1/6 times 1/5 times 1/4, which is 1/120. But that's not the answer. Remember to multiply by this 6. It's important to make sure that you circle this or write it on the top left corner or something so that you always remember. So we multiply by 6 to get 6/120, which gives us 1/20. Our answer is C for this problem. Problem number 19. Suppose that S is a finite set of positive integers. So we always want to underline the important words. Finite, which means that there's not an infinite number of numbers, which makes sense. And positive integers. If the greatest integer in S is removed from S, then the average value or the arithmetic mean of the integers remaining is 32. If the least integer in S is also removed, they italicized it, so we should probably underline it. then the average value of the integers remaining is 35. If the greatest integer is then returned to the set, so this means that only the lowest number is taken out, the average value of the integers rises to 40. The greatest integer in the original set S is 72 greater than the least integer in S. What is the average value of all the integers in the set S? So now this question, they've given us a lot of information, probably enough to solve the problem. But what we need to do is actually come up with some equations for this to solve it. So let's assign some variables. Let's let k equal the number of integers there are. So let's let the number of integers equal k plus 2 to make it more easier for us, and you'll see why in a second. So in the middle, so this is the least number, then we have a set of numbers here, and then we have the greatest number. In the middle, the sum of these numbers is, since the mean is 35 when we remove both the least and the greatest, and there's k numbers here because k plus 2 minus 2 equals k, the sum of these numbers is 35k. So now we have that, let's call this number z for now. We have that z plus 35k, so this is when the greatest integer is removed, over k plus 1 is equal to, they tell us 32. Multiplying both sides by k plus 1. So make sure that how you see this. Basically, I added all the terms and divided by the number of terms to find the mean. And I did this for all the terms except for the greatest term. And they told us that this mean is 32. So I multiplied by k plus 1 on both sides to get z plus 35k is equal to 32k plus 32. Now, bring this 35k to the right hand side by subtracting it from both sides. And we get 32 minus 3k is equal to z. Okay then. So that means that this least term, we can replace it instead of z, because we want to minimize the number of variables that we have. Instead of z, we have 32 minus 3k. Which also tells us one more thing, that 3 is anywhere from 1 to approximately 10. So that means that this set isn't that big. Now we'll do the same thing on this right hand side. So we have that once we put the smallest number back, the average is 40, which means that the average of all the numbers except the smallest is 40. So we have that 35k plus, let's let this one equal z again, 35k plus z over k plus 1, since that's the total number of terms, is equal to 40, or 35k plus z equals 40k plus 40. Subtracting 35k from both sides, we get 5k plus 40. So this term is 5k plus 40. Okay. But wait a second. Adding all of these up, this gives us a very important equation. So we know that 5k plus 40 minus 32 minus 3k is 72. Because the greatest integer in the original set is 72 greater than the least integer. And that's the last piece of information that they gave us. So what we see now is 5k plus 40 minus 32 minus 3k. But since we're subtracting a minus, it becomes positive, so 3k equals 72. So we have 8k plus 8 equals 72. Dividing both sides by 2, dividing both sides by 8, we get k plus 1 equals 72 divided by 8, which is 9, or k equals 8. Or that there's a total of k plus 2 terms, so there's 10 total terms. So now let's add up the sum of all the terms. We have 8 35s in the middle. 8 times 35 gives us 70 times 4, 140 times 2, or 280. Plus this last term is 5k plus 40, or 5 times 8. 5 times 8 plus 40, which is 40 plus 40, or 80. Plus this first term, which is 32 minus 3k. So 32 minus 3 times 8, which is 24, which gives us 8. So we have 280 plus 80, 360, plus 8, 368, divided by 10. Well, that just simply gives us 36.8. So that's our answer for this question. So during the actual test, you can double check this if you have enough time, but we won't do that here. The way you can double check it is actually looking at these values. So if you have 35K, and I think the last value is 80, and you can actually try finding the mean of each of the conditions that they specify and seeing if it equals 32 or 35 or 40. But rest assured, in this case, it does. Problem number 20. The figure below is constructed from 11 line segments, each of which has length 2. The area of pentagon A, B, C, D, and E can be written as the square root of m plus the square root of n, where m and n are positive integers. What is m plus n? Now for this problem, it's just the area of a pentagon with all the sides of length 2. And then they drew all these lines in the middle, which are supposed to help us out in some way. But what you'll see is that they don't actually help us out too much. Like, they do give us central information, but we can actually remove them at the end to actually solve the problem. Notice that this triangle right here, A, B, to this point, and back to A, is an equilateral triangle, because each side is equal to 2. That means that each angle in that triangle is equal to 60 degrees. Similarly, this angle is 60 degrees. Try to figure out why that would be 60 degrees if you don't understand why. This would be 60. So all the angles that are part of an equilateral triangle are just 60. And so on. And now we can solve this problem. So I'm going to erase this one, because those two are the only angles that we'll need. We'll draw this line in. And symmetrically, we'll draw this line in. And no, that isn't necessarily a straight line. This part isn't necessarily a straight line. I'll make it a bit more obvious. Okay. So now, this is the same as finding the area of triangle ABC, AED, and ACD, and adding them all up. Now this is a triangle which has a lot of 30, 60, 90 triangles, which helps us a lot. And you might want to review those if you don't know what they are. So this angle right here is 90 degrees. Now we know this angle right here is 30 degrees. So what we can do here now is we know that ED equals 2. Since the angle, the side opposite the 30-degree angle is half of the hypotenuse, that would be 1, and this would be root 3. Similarly, this would be root 3 since this is 2. So now we can find the area of this triangle. This is just a triangle with height 1 and base 2 root 3. So this is 2 root 3 times 1 divided by 2. And since there's 2 of these triangles, one on the other side, the 2 would cancel out, and we would just be left with 2 root 3. Now, this isosceles triangle in the middle. Well, we know that AD is equal to 2 root 3. And dropping the perpendicular height, we know that CD, let me label this, CD is twice of ED. So this right here is 1, since CD is 2. So we have right triangle AED with AD equals 2 root 3 and ED equals 1. So then AE is just equal to 2 root 3 squared, which is 4 times 3, 12, minus 1 square rooted. So the square root of 11. AE equals the square root of 11. Now we multiply this by 2 since CD equals 2 and divide by 2 to get the square root of 11. So the total sum is just 2 square root 3 plus the square root of 11. We can move this 2 inside the square root because that's how they want the answer, to get the square root of 3 times 2 times 2. So inside we would double the number of 2's there are. 3 times 2 times 2 would give us 12 plus the square root of 11. And that's it. 12 plus 11 gives us 23. And that's how simple problem number 20 was. Problem number 21. A square piece of paper has side length 1 and vertices A, B, C, and D. As shown in the figure, the paper is folded so that vertex C meets edge AD at point C prime, and edge BC intersects edge AB at point E. Suppose that C prime D equals 1/3, So they tell us C prime D equals 1/3. What is the perimeter of triangle AEC prime? Okay, so now this is an interesting problem, and we do use a lot of key facts that pertain to folding over paper or folding over anything basically to solve this problem. The first thing that we will use is the fact that angle BCD is a right angle. Now, when we fold BCD, this half of the paper, or not exactly half, but when we start folding from this side, the angle wherever we fold it to is also going to be a right angle. More specifically, EC prime, and let's call this point T. EC prime T is also going to be a right angle. Okay, so now we can continue. Maybe let's let this equal x. That might lead somewhere. So this is 1 minus x. And you might not see a way to continue here. The next thing that you have to notice here is that when we fold this piece of paper over, TC and TC prime are the same, because when you fold something, distance still stays the same. So this is just 1 minus x. And now you know what we can do. We can use the Pythagorean theorem to calculate the value of x. So we have one triangle CDT is a right triangle. So using Pythagorean theorem on that, we have 1/3 squared plus x squared equals 1 minus x squared. This is 1/9 plus x squared. And 1 minus x squared is just x minus 1 squared. Using our a plus b rule from before, we have x squared minus 2x plus 1. Thankfully, the x squared term cancels out, and we're left with 2x equals 8/9. We added 2x to both sides and subtracted 1/9 from both sides. So x equals 4/9. So now I'm going to erase a lot of this stuff. So we know that this is 4/9, this is 5/9 because this is 1 minus x, and this is 5/9. Okay, but that's not the triangle we're trying to find the perimeter of. So the triangle that we're trying to find the perimeter of is triangle AEC. Maybe we can try similar triangles, but we have to prove that. What if we let this angle equal x? Then this angle would be 90 minus x, right? Because the whole thing is a straight angle, and straight angle minus 90 minus x gives us 90 minus x. Since CDT is a right triangle and CDT is a right angle, this is x. And similarly, this is 90 minus x. And that's it. We just found an angle by AAA similarity. So, let's write that down. We have that triangle A, E, C prime is similar to triangle D, C prime, T. Interesting. Well, we also know the length of AC, so now we can find the ratio between these triangles. We have that AC prime over DT is equal to 2/3 over 4/9. Multiplying both the top and the bottom by 9, we get 6 over 4 or 3 over 2. Once again, this is pretty interesting. So how can we continue here? So we have AC prime and DT. So the ratio for triangle AEC prime to triangle DC prime T is 3:2. Well, we already know the perimeter of triangle C prime DT. We can add up all three sides to get 5/9 plus 4/9 plus 1/3, which would give us 9 over 9 plus 1/3 or 4/3. Now, the perimeter of that, the perimeter of AEC prime is just 3 over 2 times this, because perimeter is the same ratio as the ratio of the sides. If it was area, we would square it, but we're not doing that here. So we can just multiply with this by 3 to get 4 over 2, which equals 2, giving us an answer of A. A pretty easy problem for number 21. Problem number 22. Ang, Ben, and Jasmine each have 5 blocks, colored red, blue, yellow, white, and green, and there are 5 empty boxes. Each of the people randomly and independently of the other 2 people places one of their blocks into each box. The probability that at least one box receives 3 blocks, all of the same colors, is m over n, where m and n are relatively prime positive integers. What is m plus n? Okay, so we have the colors RB, red, blue, yellow, white, and green. So we'll just call it by the first letter of the color, since they're all unique. So we have R, B, Y, W, and G. Okay, so let's just assume as any possibility for Angelina, or for Ange. Let's say there's red, blue, yellow, white, and green. So she puts the red in box 1, blue in box 2, and so on. It doesn't matter what she does when we're determining our probability, because all the cases are going to be symmetric. Now we can do casework on what Ben decides to do, and thus what Jasmine will have to do to make it so. But first, we'll apply a tool called derangements and complementary counting. So instead of figuring out how many ways there are for at least one box to receive 3 blocks of the same color, we'll figure out the number of ways that there's for no boxes to receive 3 blocks all of the same color, and then subtract that from 1 at the end to get our answer. The number of derangements of an element set, which is represented with this factorial symbol but before the number, is just the number of ways that you can have a permutation of n things where none of the elements are in the original order. For example, a dearrangement of R, this would be if R was in box 1 and B was in box 2, and so on. Then a possible dearrangement would be R, B, Y, W, G. Nothing is in their original order. So there are a lot of formulas for calculating this, but basically you should just memorize the first few values. So we'll be using the fact that the dearrangement of 5 things is 44, the dearrangement of 4 things is 9, and the dearrangement of 3 things is 2. Okay. Now we can proceed with casework on the number of things that Ben has in common with Ing. Let's say there's 0 things in common. So let me write 0 here. If there are 0 things in common, then how many ways can I do that? Well, that's just the dearrangement of 5 things, which is 44. And since there are no things in common, regardless of where Jasmine decides to put her stuff, it will work. So she has 5 factorial ways, or 120 ways. What about 1? Okay, so there are 5 choose 1 ways to pick the color that they'll have in common. Now we multiply this by, for the other 4 colors, the number of ways for it to not have anything in common, or the dearrangement of 4, which is 9. So we multiply this by 9. Okay, so now we're basically looking for the number of ways that Jasmine can put her stuff without it being in any of the common elements. So without any of the boxes having 3 elements of the same color. How many ways can she do that? So we can sort of just assume that R is the common one. It doesn't really matter which one is the common one, since we already have this 5 choose 1 term. After this, we're looking for any generic dearrangement. Maybe Y, B, G, and W. That's a valid dearrangement. Now, how many ways can Jasmine continue here? How many ways can she pick a box? So she can't have a R in the first box. That's the only condition. So if we start with the number of ways that she can pick where the R goes, that's 4, because she can't put it in the first box. Now the second color doesn't really have any conditions on it, so it has 4 ways since one of them is already taken. All the way times 3 times 2 times 1, so 4 factorial. So this is the number of ways with 1. Now the number of ways with 2. First, we have to pick the 2 colors that will be in common, so that's 5 choose 2. Second, the other 3 colors that are left should not be in the original squares, so the dearrangement of 3 is just 2. Okay, now we proceed a bit with casework. So let's say the colors that were in common are R and B. So then we have R, B, Y, W is G, and R and B come here. Now let's proceed with any standard D arrangement. We already counted all of the D arrangements in that ×2 and all of the possible color combinations in the 5 choose 2. So it doesn't matter what we pick. So we could have a W here, a G here, and a Y here. That seems to work. How many ways can C go now? So C, let's say C decides to put the R first. If the R is here, then second, if they decide to put the blue in, the blue can go anywhere. There's 4 choices for the blue. So there's 4 choices for the blue. Let me write it right here. There's 4 choices for the blue. And then there's 3 factorial ways of the rest. So 4 times 3 factorial. Plus, what if, plus, R could go under the W, the G, or the Y in the same box as them. Then what? So we have 3 choices there for which one it goes under. Then B, it can't go under the box that red is already in, and it can't go under the second box because that's where the blues are. So that's 3 choices left. Then for the other 3 colors, there's 3 possible choices left. 3 times 2, 6 factorial, so 3 factorial here. So that's what we get for this case. Okay. Let's look at the case where there's 3 colors in common. How would we continue there? If 3 colors are in common, then what? Then we have 5 choose 3 ways of picking the 3 colors that will be common. Now we proceed once again with assuming one case that's true. For example, let's suppose that Ben and Ing have RB and let's say they have RB and G common. So then let's write it. So we have R, B, G, and maybe we could have a Y and a W here. And then Ben also has R, B, and G, and then he has to have a Y and a W and a Y here. So now what? Suppose that W and Y both end up for Jasmine in one of these 3 spots. How many ways can that happen? That can happen in 6 ways because there's 3 ways to pick where the W would go and 2 ways to pick where the Y would go. So which would leave 2 spots for the color that didn't get occupied. For example, if W is on R and Y is on B, then G can go either on W or Y. So that would give us 2 spots for that. And then after that, we'll have 2 spots left for the other 2 colors, right? Because R can go to G or W, and then B is already decided. So that would give us 6 times 2 times 2. 6 times 2 times 2. If only one of yellow or white or Y or W occupies one of the RBG spots, how many ways can that occur in? Well, there are 2 ways to choose which one from Y or W, and 3 times 2 spots to choose for both of them. And this leaves 3 ways for the rest, or 2 times 3 times 2 times 3. Finally, if Y and W stay in these 2 spots, there are 2 ways to assign them, and 2 ways to assign R, B, and G for 2 times 2. This would give us a total of 24 plus 2 times 2 equals 6, 6 plus 2 times 3 equals 36, 6 times 3 equals 30, 6 times 6 equals 36, and then 2 times 2 gives us 4. That is 64. Okay, so that means that we multiply by 64. So I'm going to erase all of this. And write 64 here. If I choose 3, it's just 10. Finally, 4 colors is impossible because then where would the 5th color go? That would be there. So instead, we go straight to 5 colors. Now here, basically, if Ing and Ben are both on the same colors, then basically Jasmine can't have any of them in that original spot, which is just the D arrangement of 5 or 44. And now we proceed to add up all of these. Let's now do that. So I went ahead and cracked out the multiplication. You could do it on your own. It's not that extensive. And now let's add up all of these terms. So we have 5280 plus 4320, which gives us 0016960 plus 1560 equals 61 here, and we have, let's see, we would have 11 here. Adding in 640 plus 44, that's 688. So 1160 plus 688 would give us 8418 and 11. Okay. So what's our denominator? Well, we already fixed the number of ways with A, so that didn't even count. We basically had 120 ways to arrange for B, for Ben, and for Jasmine. So that's 120 times 120. That would be 12 times 12, which is 144. And then we add 2 zeros to the end, which is 14400. So our answer is 14,400. But remember, we have to subtract this from 1. So what we do is 14,400 minus 11,848 over, let's see, so that would be 10 minus 8, which gives us 2, 10 minus 5, which gives us 5, 14 minus 9, which gives us 5 again, and 14 minus 12, which gives us 2. And we're dividing this by 14,400. And this, do it yourself, would be a good exercise just to make sure that you don't make silly mistakes, which were pretty common in this problem. But that would just be 71 over 400. 71 over 400. Adding up the numerator and the denominator, like we were supposed to in the problem, our answer would be 71 plus 400, 471. And that is problem 22. A square with side length 8 is colored white except for 4 black isosceles right triangles with legs of length 2 in each corner of the square, and a black diamond with side length 2 square root 2 in the center of the square, as shown in the diagram below. A circular coin with diameter 1 is dropped into the square and lands in a random location where the coin is completely contained within the square. The probability that the coin will cover part of the black region of the square can be written as 1 over 196 times a plus b root 2 plus pi, where a and b are positive integers. Find a plus b. Well, after you're done reading this long problem, make sure that you reread it to make sure that you don't miss any information. And then either print the test or draw the diagram on paper. We decided to make the diagram even bigger and try to solve this problem. So now it's very hard to try and tackle a problem with involving circles and just like deciding where the circles are going to be placed. Instead, we're going to be looking at the center of the circle. You should realize that the radius of the circle is 1/2 since the diameter is 1 and we divide by 2. So now we're trying to find the center of the circle and place it somewhere so that it covers some part of the black region. But first, notice that if the center of the circle is 0.5 near any of the sides, it'll have some part of the circle that's outside of this square, which is not allowed since it should be completely contained. So it should be at least 0.5 away from both sides, which would give us a 7 by 7 square. So in this geometric probability question, our denominator would be 49, which makes sense since 49 is a divisor of 196. So let's start with this middle rhombus. Either the center could be inside this, which would be 2 square root 2 times 2 square root 2 since it's a square. So that would give us 8. Or it could be 0.5 away from each side like this. And that would give us 0.5 times 2 square root 2. So make sure you see why this makes sense. Like for example, if it's here, this would be in the square itself, which is dark. So that's why it works. So that would be 0.5 times 2 square root 2, which is square root of 2. And since there's 4 sides, for example, one right here, since there's 4 sides of this rhombus, we get 4 square root 2 here. Now, we have these quarter circles, and there's 4 of these quarter circles. And if the center of the circle is in these quarter circles, it's also going to hit part of the rhombus. And that's just a quarter circle with radii 1 or radius 1/2. And that would be 1/4 pi. Since there's 4 quarter circles, that's 1 full circle. So we just add 1/4 pi here. Now comes the harder part. Now we drew a line 0.5 away from this isosceles right shaded triangle. And then we drew 2 lines connecting it to make it into a rectangle. Now what we're going to do is just find some points. First of all, we know that this is 2 because they tell us this is 2, 1, 1, using the Pythagorean theorem, root 2. And using the Pythagorean theorem for this 2, 2 triangle, this whole thing would be 2 square root 2. 2 square root 2. We subtract the root 2 in the middle to get root 2. And since these segments are equal by symmetry, it's root 2 over 2 for each of them. So let me write it here. Root 2 over 2. We'll just look at this one side for now. We also know that this right here is 0.5. Now what we can do is extend this side and this side until it hits that. So now notice that this is a rectangle, so this is 90 degrees. And you can also prove it more rigorously by saying this is 45 degrees and this is 45 degrees. And since it's a straight angle, that rectangle angle should be 90 degrees. This is a 90 degree angle, and it's this triangle right here is a 45, 45, 90 triangle. I want you to prove why that's true, but I'll give you a hint. This is a 45 degree angle, and this is then a 135 degree angle because of transversals. How can we use that to prove that this angle right here is 45 degrees? Okay, so we know that. Now what else do we know? So since it's an isosceles right triangle, this thing right here is root 2 over 2. I'll draw it a bit farther away so that we'll know. Root 2 over 2. Okay, now we think, how can we continue? How can we continue in this problem? Which segments work? So basically, we're trying to find which segments would work for the centers. Where can the center be located so that it would work? So what we would do next is, so now what we do is, we realize that this part right here, we already said this is 0.5. So this part right here, this very small part, and yes, we're getting very small, but you can zoom in on a real sheet of paper. Bring it as close to your eyes as you need. But this is root 2 over 2 minus 1 over 2, since 0.5 is 1 over 2. So this is a right triangle, 45, 45 again. So what we have is this part right here. That part right there is once again root 2 over 2 minus 1/2. And it's a 45, 90, 45 triangle. So to find this part right here, we multiply this expression times root 2, which would give us 1 minus root 2 over 2, or 2 minus root 2 over 2. So that's the area of that. And we would subtract this from 2, which is the length of the leg of the black triangle, to get the leg length of the desired region. And 2 minus this thing right here would give us, this would become positive. This would basically become 4 over 2 minus 2 plus root 2, and this 2 is everywhere. So this would become 2 plus root 2 over 2. So that's the side of this triangle region that works. And it's an isosceles right triangle, so we can square this and then multiply by 1/2. So squaring this, we get, using the a plus b squared formula again, 4 plus 4 root 2 plus 2 over 4 times 1/2. This gives us 2 plus 2 root 2 plus 1 over 2 times 1/2. Now, we need a bit more space. So what we realize next is that 2 plus 1 gives us 3. 3 plus 2 root 2 gives us 1/4. And that would give us, let's see. So we would get okay. So yeah, right here we would get 3 plus 2 root 2 over 2 times 1/2. This would give us 3 plus 2 root 2 over 4. Okay, so now since there's 4 of these regions, remember that there's 4 of these regions, one on each side, you would multiply this by 4 so the denominator would cancel, and we'd get 3 plus 2 root 2 here. So this would become 11 plus 6 root 2. This would become 11 plus 6 root 2. And once we get 11 plus 6 root 2, we add in 1/4 pi over 49. So now we factor out a 1/4 because the denominator is 196, which is 49 times 4. So then we would get 1 over 196 plus 44 plus 24 root 2 plus pi, which matches the problem conditions, and we're just doing 44 plus 24, and that would give us 68. Let's see if that's an answer choice, and sure enough it is. And that's how we would solve problem number 23. Problem number 24. Arjun and Beth play a game in which they take turns removing one brick or two adjacent bricks from one wall among a set of several walls of bricks, with gaps possibly creating new walls. The walls are one brick tall. For example, a set of walls of sizes 4 and 2 can be changed into any of the following by one move: 3, 2, 2, 1, 2, 4, 4, 1, 2, 2, or 1, 1, 2. Arjun plays first, and the player who removes the last brick wins. For which starting configuration is there a strategy that guarantees a win for Beth? So once again, we have to use the answer choices for this problem. Let's take a quick look at them. 6, 1, 1, 6, 2, 1, 6, 2, 2, 6, 3, 1, 6, 3, 2. Now, we notice that all of them have 6 as a common term, so let's try playing around with this 6 diagram. If Arjun goes first, he might want to try forcing symmetry. Like, if he can cause it into a position where he can just mirror whatever Beth does, he'll take the last piece and win. And the way he can do that is by taking out this middle 2. Once he does that, whatever Beth picks, he'll just mirror that. So for example, if Beth picks this one, then Arjun can pick this one. And if Beth picks this one, the one to the right of that, then Arjun can just pick the one on the opposite side. Basically, whatever Beth does, Arjun would just mirror that, and he would get the last turn. So we need some other set of bricks, which we do have, that will make sure that this symmetry doesn't happen. Well, if we have 1, 1, now once again, Arjun will just take the middle, and whenever Beth decides to take one of these, if she eventually does, then Arjun will just take the other one, and he's forced to symmetry again. But let's look at 6, 2, and 1. Okay, what can we do here? So this looks interesting. Now, if Arjun tries to force symmetry like he did in the previous example in the middle, then Beth could just, after the thing in this 6 block has been exhausted, could just take one of these bricks, and now she's forced the symmetry onto Arjun. So this seems pretty interesting. Let's see. We'll take a look at the other answer choices, but let's see if there's any way for Arjun to win here. Anything that we can see. If Arjun takes the block all the way on the right, then what? Let's say Arjun takes this block right here. What can we do then? How can Beth force symmetry? Or if she can't, then how can Arjun force symmetry after that? That's what we're looking for. If Beth decides to take both of these blocks, then Arjun will be left with a 6 block, which we already proved is a win for him. But what if she decides to take only one of these blocks? Well then, if Arjun decides to take the middle with symmetry again, basically this position is 6,1, and if Arjun decides to take the middle again, then this time when the 6x1 is done, we'll be left with this one block which Beth can take to win. So this would also be a win. And similarly, if Beth takes this one. What if Beth takes anything in the 6x6 grid now? I mean, what if Arjun takes anything in the 6x6 grid? We already proved that the middle won't work because it'll force a symmetry, but it'll be bad for Arjun himself. What if Arjun takes this one? Okay, well, then we have symmetry once again. Beth can just take this one. And now we have a 1, 2, 1, 2, 1. And now whatever Beth does, whatever Arjun does, and Beth can just copy that. And eventually at the end, there'll be one left over that he can win by. She can win by. Okay, so this seems like a guaranteed win for Beth, but we want to check the other answer choices. Well, 6, 2, 2, we can already see that won't work. And the reason being is if we have a 2x2 here, this once again forces symmetry. If Arjun takes the middle 2 like he's been doing, then this is symmetric. Whatever Beth does, Arjun can copy the same and get the last piece. So that is not a win. What about 6, 3, 1? What can we do here? If Arjun decides to take anything from these two squares, then basically that's what we have to analyze. What if Arjun takes the square all the way on the right? Then Beth, how can Beth continue? So if Arjun takes this square, how can Beth force symmetry? And the way she can force symmetry is by taking these two middle again. And then whatever Arjun does in the 6x1 block, Beth is going to do the same. And this block right here will take 2 turns to get exhausted. So that won't work. Okay. And now what if Beth decides to take one block, or Arjun decides to take one block from here? Well, then we just have a 6, 2, and 1 combination, which we already proved is a win for, or which we think is a win for Beth. Because she'll have that position then. Okay. What else can we play here? Anything else? What if we take 2 from here? If we take 2 from here, then we're in that position 6, 1, 1, where it's Beth to move now, and we already said that 6, 1, 1 is a win for whoever moves first. So that would be a win for Beth. Similarly, if you continue, you'll see that it won't work. We'll leave it to you to prove the other choices, but that's how you would continue proving this. And basically your answer would be 6, 2, 1. Okay. Problem number 25. Problem number 25. Let S be the set of lattice points in the coordinate plane, both of whose coordinates are integers between 1 and 30 inclusive. So that's just a lattice point. Coordinates where both are integers. Exactly 300 points in S lie on or below a line with equation y equals mx. The possible value of m lies in an interval of length a over b, where a and b are relatively prime positive integers. What is a plus b? Now you need a bit of guessing to get this problem started, and you have to realize that 2/3 work. That seems like a number that would work, and it does work. And the way we prove that is every time the line intersects one of the points, we'll add those up. So we get 1, 2, 3. That's 3. Then we get 1, 2, 3, 4, 5, 6, 7, 8, 9. So the next one might be 27, but let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, it's actually 15. And now we start seeing the pattern. The common difference is just 6. And this is just the arithmetic sequence. Since there's 30 total elements, or 30 along the x-axis, and we're doing this every 3, we do 30 divided by 3 to give us 10. So we're looking for 3 plus 3 times, so we're just using our arithmetic series formulas here. You can watch our video on that if you don't know what those are. 3 plus 3, so 6 times 9 plus 3. And we multiply, so this is the 10th term and that's the first term, and we multiply this by 10 and divide by 2. This is 54 plus 3, 57 plus 3 equals 60 times 10 divided by 2 equals 300. So that works. We just proved that works. Now what? There should be more that work, otherwise our answer would be 0, which isn't even an option. Well, what if this slope is less than 300? If the slope is less than 300, right now we have exactly 3 points, 300 points. And some of these points are directly on the line y equals 2/3 x. So if we have it less than 2/3, some of these points won't be included. And if some of these 300 points are not included, we will have less than 300. And there's no other points that we can get that are not counted in these 300. So since we'll have less than 300, that will never work. So our minimum is 2/3. What about our maximum? Now our maximum, well, for our maximum, we have to realize one thing. Any line above this slope 2/3, if it goes through any other point other than these 300 points, it'll be more than 300 points, which is not allowed. So we need a line that when we're going through it, even if it goes over 1 point, it doesn't work. And that's what we're looking for. That would be the number that does not work. Hopefully that makes sense to you. We're looking for a line that does not go through any lattice points other than these 300 points. So it should not contain any points other than these 300 points. And the only points that line would contain other than these 300 points are the lines where the points are directly on that line itself, if it's very close to 2/3. We also know that the denominator itself must be less than or equal to 30, but less than 30 since 30 is a composite number. Although it might be 30, we do have to double check that since we're talking in a 30 by 30 grid. So let's see. If we have a 30 over this, so we basically need one other point more than the 300 that we already have. And as long as our slope is more than 2/3, so more than 20, we should have at least 300 points. So 20 over 30 simplifies to 2/3, so that doesn't even count. 21 over 30 is equal to 7 over 10. So that's way too many points. That's just going to be way too many points. 22 over 30 would also be way too many points. If anything is not relatively prime to 30, that won't work. 23 over 30. How many points does 23 over 30 have? It would have all of these 300 points, and it would also have the point, if this is x equals y, it would also have the point 30, 23. Now make sure that we don't cover 30, 23 here, and we don't. Okay, so 23 over 30 could possibly be an upper bound. What about something over 29? Let's see. Well, 29 times 2/3, what does that give us? That gives us approximately 58 divided by 3. So what can we do here? Once we have 58 divided by 3, this is just a bit less than 20. And since we're looking for integers on the top, we can have a 20 here. But that covers one more point. So 20 over 29 works. That would also work as an upper bound since that's not a valid slope. What else can we do? Let's go to 28. 28, we would have 28 times 2/3, which would give us 28 times 2, or 60 minus 4, 56 over 3, which is a bit less than 19. So we could have a 19 here. That would work, since that would have the point 19 over 28. So that would have 301 points. So anything below 19 over 28 should work. Let's drop it down a bit more. If we have a 27 here, and then we put anything above 18 here. So if we have 19 over 27 here, since 18 over 27 is 2/3, if we have 19 here, that works, but that upper bound is it's like 19 over 28 is a better upper bound, since, going back to the original problem, the possible values of m lie in the interval of length a over b. So if 19 over 27 works, that's automatically included in 19 over 28. So our upper and lower bound is 2/3 and 19 over 28. Now you can do this subtraction on your own, or we'll do it right here. We'll get 28 times 2 minus 19 times 3 over 28 times 3, which is 84. This is 56 minus 57, which would give us the expression. So this would give us minus 1, since 56 minus 57 gives us minus 1 over 84. Since distance is always positive and length is always positive, this is just 1 over 84. 1 plus 84 equals 85. And that's how you would solve problem number 25. Both on the AMC 10A and on the both on the AMC 10B and on the AMC 12B. That's it. We just went over all the solutions from the 2021 AMC 10B. If you have a different solution, feel free to comment it down below. Thank you for watching this video. If you liked this video or learned anything from it, let me know by subscribing or commenting below. For more awesome content, check out thepuzzler.com. You'll find amazing articles and free courses there. Thank you.